Alright, this is Algebra 2, Chapter 6, Section 1. Happy New Year. Uh, Here we have some expressions that you guys had learned in Algebra 1 in terms of multiplying and dividing exponents and certain common uh, exponent properties, such as a to the 0 is 1, uh, for a being 0, of course, non-zero. If I have two exponents with the same base, different exponents, and I divide them, I subtract their exponents. A number raised to the negative exponent is the inverse, and once you flip it, the negative sign goes away. You have n in the parentheses, and they have two products. You raise them both to the same power. When you have some base raised to a power times an exponent, you multiply their exponents. When you multiply the same base times two different exponents, you add them. And when you have a fraction raised to an exponent, that exponent carries to both the numerator and the denominator. If you want to practice on your own, you can use this here, and there's some practice questions here, and feel free. 6-1 sort of expands on that exponent and say, okay, what about when the exponent is a fraction or a square root or a root? Okay. If I square 5, I get 25. If I cube 5, I get 125. If I fourth root it, I get 625. And if I 5 root it, I get 3125. Meaning, if I do the opposite and say the square root, I would get 5. If I do this and call that the cube root, I get 5. If I do this, I get 5. And if I do this, 31. That's the fifth root. I get 5. Meaning that if I multiply 5 times 5, I get 25. If I get 5 times 5 times 5, I get 125. If I get 5 times 5 times 5 times 5, I get 625. I get 5 times 5 times 5 times 5 times 5. I get 3125. Alright, this is a 5, 4, 3, 2. This is a square root. This is a cube root. So fourth root is a fifth root. Meaning, if I multiply the same number 5 times, then I get 3125. 4 times 625, 3 times 125, 5 times 25, etc., etc., etc. And we have an overall concept for that. And here it says if a is to the n and a and b are real numbers, and n is a positive integer, and then a is the nth root of b. A is the nth root of b. Meaning, in this case, 5 equals a, right? And 5 to the n equals b. So if we say 5 to the 5th power, that's going to give me my 3125. Meaning that this a, this 5, is my square root, or in this case, the 5th root. That's all it means. It's a fancy way of saying that that's the root. I don't really think of it in that way. Maybe because this is one of the few times where I'm like, calculator is a good thing. Um, if n is odd, there is one real nth root of b, denoted in the radical form of as n uh, root b. If n is even and b is positive, there are two real roots of b. The positive root is the principal root, nth root, and the symbol is uh, root n root b, and the negative root is its opposite, negative n root b. And if b is negative, there are no real nth roots. All right, so what does all that mean? Let's talk about it. Let's use cube roots. So this is a cube root. Um, let's use, let's see, 3 times 27, and that's and let's use negative 27. If I was to cube root it, this would be 3. If I was to, and that's because 3 times 3 times 3 equals 27, so it would be 3. If I was to cube root a negative number, this case would be negative 3, because negative 3 times negative 3 times negative 3 equals negative 27. So when n is odd, this is what this is saying. When n is odd, there's one real root, nth root of b, denoted by the radical form n root b. That's all this means. That's all this means. This would be n root b, and then this would be my one real root. So this is n, this is b. That's all it's saying. Uh, if it's a negative number, it would also be whatever that root would be, negative. This is just a fancy way of saying that we can have negative roots. When it's odd, when you're cubing, or when it's to the fifth, or when it's to the seventh, or when it's to the ninth, you can have negative roots. That's what this is saying. However, we already know that when it's even, it's different. So if we have square root of 81 and then square root of a negative 81, we know that this is going to be plus or minus 9, where the plus 9 is called the principal root. And it's only called the principal root because it's positive. That's really it. And the negative 9 is just the other root. They don't even give it a name. I'm pretty sure they give it a name, but they don't really think that it's important here. So we have two, and they call this two real roots. And what they mean by two real roots is that there's no imaginary numbers. Okay. Here we have the square root of 81, and we would have to say that it's 9i, right? We've learned that. But this is not a real root. This is a complex number. So we don't even go to the whole 9i thing, and we just say that there are no real roots. So for this chapter, we're not going to really do the imaginary thing, or at least for this section, we're not going to really do the imaginary complex number thing. Where if we see a negative, positive square, so this could be 2, 4, 6, 8, etc. We just say there's no real roots and we leave it alone. We don't convert it into imaginary. B is negative. There are no real roots. We leave it alone. Right, so that's what this concept is talking about. Odd numbers, you can have negative roots. Even numbers, if it's a positive, you only have two real roots, positive plus minus, and if it's negative, you can't have a root. That's real. All right, vocab time. They should have did this first instead of describing roots, but okay. This guy is called the radical symbol. Okay, yeah, got that. Then this guy down here underneath or inside the radical symbol, that's called the radicand. Radicand, whatever is being rooted. And then in this guy, whatever this thing could be, square root, cube root, fifth root, fourth root, etc., that's called the index. And that tells you how many times you're rooting. So we have the radical symbol, the radicand inside the radical symbol, cand, and then the index. Yeah? All right. All right, finding roots. So they want the fifth root of 0. That's 0 because 0 times 0 times 0 times 0 times 0 equals 0. They want the fifth root of -1. Now, since this is an odd index, then I can have a negative answer. So this would be -1 because -1 times -1 times -1 times -1 equals -1. And then fifth root of 32, I think it's 2. Let's see. Yeah, equals 2. Well, plus and minus 2. Because 2 times 2, actually no, this is an odd number, so this is not plus or minus, just 2, sorry. 2 times 2 times 2 times 2 times 2 equals 32. Okay. For B, they ask what are the real square roots of these numbers. What's the square root of 0.01? And I believe that's 0.1. Because 0.1 times 0.1 equals 0.01. Square root of -1. Now we would say 1i from chapter 5, but we don't have to actually focus on the I. So we'll say no real roots. That doesn't discount the complex number. We just acknowledge that there are no real roots, no non-complex roots. All the answers would be in the form of imaginary. Square root of 32. Sorry, square root of 36 over 21, 121. When I see something like this, I notice that they're both perfect squares. So I can say that this is square root of 36 over square root of 121, which gives me 6 over 11. So since it's a positive, I can say plus or minus 6/11. All right. Fundamental theorem of calculus says that this has 4 roots, only 2 of them which are real roots. And like I said, we're not going to focus on the imaginary roots. So this is a fancy way of saying, remember we said that there's there's actually a root there. We're not going to focus on the imaginary roots today. All right, finding roots. So cube root of negative 27 is going to be negative 3, because negative 3 times negative 3 times negative 3 equals negative 27. Yay. The cube root of negative 81. No real roots. And again, that's because 4 is an even number. So they would all be imaginary. And we're not dealing with imaginary in this particular section. C, square root of negative 7 squared. And I know what you're thinking. Oh, it must be because there's a negative in there. But notice that this negative number is being squared first, then square rooted. So we are going to say that this is the square root of 49, not negative 7. And then that would give me plus or minus 7. So that square kind of ruins the deal. D, root negative 49. Again, can't do it. No real roots. No real roots. Okay. Simplifying radical expressions. Okie dokie. So the way they do it is a little bit different from how I think about simplifying radical expressions. And I'll explain what I mean in a moment, which is right now. So here we have 16 x to the 8 square root. I'm going to put a 2 there to let me know that the square is, the index is 2. Since there's a 2 here, and I see that this 8 is divisible by 2, I actually divide it. I divide it by 2 in my head. So the square root of 16 is 4. It's going to be, oh, I skipped something, I'm sorry. Nth roots with nth powers. We have n, index of n, root over a to the n. If a, it's going to be a if n is odd, and it's going to be the absolute value of a if n is even. Meaning, if we have the cube root of negative 27 to the third, I should say negative 3 to the third, the answer is going to be negative 3. Right, they cancel out. However, if I have square root of negative 8 squared, these two cancel out, but this doesn't stay negative 8. I actually have the absolute value of negative 8, which is 8. And the reason why that is because since I'm squaring this guy, this turns into 64, and the square root of 64 is 8, and not negative 8. I had to get the absolute value to get to that positive 8. So they cancel each other out. So it would be the absolute value. So when they're even, the index is even, it's going to be the absolute value of whatever this is in here. When it's odd, it's just the same number. Okay. With that information in mind, go back here, 16 x to the 8 square root. So this is why the book does the whole x to the 4th squared, so that we can get to the absolute value, and they're both being absolute valued. to get to the answer. But if you have it in mind that if this is an even index, this is going to be the absolute value anyway, I know that this is 4. I divide 8 divided by 2. I repeat, I divide 8 divided by 2, and I get x to the 4th, which is your 4x to the 4th. Take the absolute value, and then it's 4x to the 4th. Down here, I have cube root of a to the 6, b to the 9. Again, I'm dividing by 3. Since this is a cube, it doesn't really matter. You don't have to absolute value anything. 6 divided by 3 is 2, so a squared. And then 9 divided by 3 is 3. So the answer is a squared b cubed. I divide by the index. It just saves time then to go through this process. And I know why it's going through the process to force you to do the whole absolute value thing. I get that. However, I think it makes it a little bit more confusing. But I mean, I understand why the book is doing what the book has to do. Alright, y to the 12. Again, I'm dividing by 4. So 8 divided by 4 is x squared. Y divided by 12 divided by 4 is y to the 3rd. Since this is a positive number, then both of these guys are being absolutely valued. But an absolute value of a square doesn't really matter. It's going to be a positive number anyway because it's being squared, so I can actually leave that alone and say that's x squared. But since this is a odd value, we're going to absolute value that guy because if I put a negative y in there, it's going to mess up the answer. So this is the absolute value of that. So that works. So after you do the roots and you get an odd number as your answer, then you an odd exponent rather as your answer, then you keep the absolute value symbol. So notice up here it says, however, absolute value of 4x to the 4th is 4x to the 4th because x is always non-negative, meaning that you do the absolute value, but if your answer is a positive exponent, you don't need to keep the absolute value. However, here, the exponent is odd, so if I put a negative number in here, this would turn it negative. So I do have to get the absolute value. I have to keep that positive so that this whole thing in here stays positive. Because I can't root a negative number. So to make sure that everything stays positive, I do have to take the absolute value of an odd exponent when it's my final answer. All right. All right, 81, x to the 4. Again, I like to put this here. I know this is 9. 4 divided by 2 is 2, so it's x squared. Absolute value, but since this x is already squared, I know that whatever number I put in here is going to keep it positive, so I say that it's 9x squared. Here, I have cube root a12, b15. Again, I'm dividing, so 12 divided by 3 is 4. 15 divided by 3 is 5. And I leave it alone. Since it's a cube index, or odd number index, I don't have to worry about absolute values. Here, I'm 4. I have x to the 12. I have y to the 16. Again, 12 divided by 4 is 3. 16 divided by 4 is 4. I absolute value the whole thing. But since this is a even number, I don't have to worry about it. Since this is an odd number, I do as a final answer. So This guy stays with the absolute value simple, and then this guy can be just 5 to the 4th point simple. Okay, I actually like this problem. This is a nice way to curve your test if one teacher was to want to curve some stuff. This would be an excellent way to do it. So we have the adjusted scores, which is equal to 10 times the square root of the R for raw scores, or the actual scores, or the score that you guys actually got. And they want what the updated scores would be from a range of 36 to 90. So if we do for R equals 36 and for R equals 90, we have two scenarios. Scenario number one, the adjusted score equals 10 times the square root of 36, which is 10 times 60. 10 times 6, which equals 60 points. Nice. And in scenario number two, adjusted score equals 10 times square root of 90, which is 10 times 9.487, which gives you 94.9 points approximately. They say about 95. Cool. Nice. Now, what if those raw scores were 0 and 100 actual scores? Which is why a lot of people use this method. A equals 10 times, so let's say R equals 0, R equals 100. So scenario number one, for R equals 0, A equals 10 times the square root of 0 equals 10 times 0, which equals 0. That sucks. And then A equals 10 times the square root of 100. Well, the square root of 100 is 10. 100. Nice. Okay. So that is this section. Happy New Year. I hope you have a great rest of your day.